Hi, everyone. So today we're going to finish our variable rate exercise. And so last time we met, we basically talked a little bit about how do we find that information of even just creating a fixed rate nitrogen recommendation for different crops in different states. Then we did a search for cotton in Georgia. We found a couple of different sources, right? So one was the Cotton Production Guide, which is a PDF available online for free that is developed by the UGA cotton team. And we also talked about UG Vertex, which is a interactive web page where you can add the different specific details of your field, of your crop, of management, where you are, um, and just entering your information, you do get a recommendation back. So we went through that. We had our quiz as well. We already talked about it. And then we got to coding. So if you can go ahead, if you don't have yet the variables in your environment, if you just want to go ahead and run the chunks, so we're first loading packages, defining our map theme here. And then one thing that we talked about is that we wanted to bring in the actual clean, wrangled, interpolated yield data for all 3 years and combine them into one data set that then we can extract the 90th quantile of all those years of yield data and set that as our yield goal, as yield goal is one of the main variables that change your nitrogen prescription. So we brought in yield data from 2017, from 2019, and 2020. If you want to go ahead and run those chunks. We also then needed to have a column describing the zones, right? So which pixel was assigned what zone. So we did that by running this chunk here and importing an object or importing a data set that we saved to an object called zone.st. And then we did some wrangling, which here basically only entails combining all these layers. So combining the zone layer with all the yield layers as well. So just go ahead and run that. So we create this object called ZoneYield. And then we were exploring a little bit here how to, like, what are we really after, but in a graph format, right? So we started with ZoneYield and we created until zone density to look at the distribution of the yield data at each one of the zones, so the high yield and low yield zone. And then if you just run this chunk right here, it's not going to run because we have not created the VRN object yet. But when we do create that, so this last line of code here basically adds vertical lines at where the 90th quantile of each one of these two distributions is. So if you run this chunk right here as is, it's not going to work because VRN has not been created yet if your environment was empty, which is my case. So for I'm just going to go ahead and to the next chunk and see what we had worked on here. So we start with ZoneYield. We pivoted that longer to have one column with all the yield values for all 3 years. Then we group by zone and summarize to get the 90th quantile of each one of those zones. And then we went to UG Vertex, entered some of the information there, and got two different nitrogen recommendations, one for the high, one for the low yield zone based on their different yield potentials. And then I also showed you a formula here that would get you pretty close to the result that UG Vertex gives for cotton in Georgia, right? So this is where we stopped. I'm just going to run my chunk until here, and I just want to show you what VRN, the object VRN is at this point. So it only has 2 rows, and that's because we used summarize right there, right? So we group by zone, and because we only have 2 zones, then summarize returns 1 row for each one of the levels of the grouping variable. So 2 zones, 2 rows. So we have our yield potential here, which is coming from the 90th quantile. We have our geometry, and then we have our total N rate needed for each one of these 2 zones. So this would be the total nitrogen that is required throughout the growing season. So if we on the cotton production guide, there is a part of it that says that if it's cotton following cotton, you should increase that rate by 25%. So on UG Vertex, if we, let me just open that so we can see what I mean. If we go on UG Vertex, let me get the website. Yeah, right here. So if we were on UG Vertex at some point, and then what I was playing around with it, and I noticed that in our case, if we have crop here being cotton, we chose coastal plain as our soil. We said it was irrigated, and prior crop. So if you leave as unknown or if you leave as cotton, it will give you the same recommendation regardless. Of course, here we were changing our yield goal. So for let's just come back quickly here and see what were our yield goals again. So let's say the high was like 2,028 pounds of lint per acre, right? So if we do 2,028, so that gives us 135 pounds of N of nitrogen per acre. And if we change this to cotton or unknown, the recommendation does not change. So it doesn't seem like it is like increasing in 25% if we have cotton after cotton. Or maybe it is, but it's just not clear. Maybe the cotton and unknown are the same. It's like just playing safe and increasing 25% anyways. But I just want to show you, so regardless of what UG Vertex is doing behind the scenes, as far as increasing or not 25% based on previous crop, I still wanted to show you, assuming that UG Vertex was not doing that, how we would do that. And I hope that that becomes helpful for you to think about this as well, in case you had to do this on yourself, on your side. So let's do that in the next chunk, or not, or in the next line of this chunk here. So if you want to go ahead, add a pipe, bring your cursor after that comment. We're going to use a mutate, right? And I want to call this next column here total and rate underscore ADJ for adjusted underscore pounds per acre. So if we want to adjust the column that we have already created called total and rate in 25%, we basically just call that column name, which is right above there. So equals that column name. And to increase this in 25%, we basically just multiply that by 1.25. If we run this and we print it, this is what we get. So it's so this new column here is the adjusted total and rate that just increased in 25% our original total rates that were based only on yield potential. Okay, so another piece, the next part here that we need to do is that, so cotton management, as you may have read on the cotton production guide, so at least, so 1/3 to a fourth of the total nitrogen rate is applied at planting or near planting, and the remaining is applied in season, right? So what we want to do here then is define how much we will apply pre-plant first, right? So let's add a pipe here, come after that next comment right there. Let's use another mutate. I want to call this next column PP for pre-plant underscore total and rate underscore ADJ for adjusted underscore pounds per acre. So the column names are getting longer, but I just want to make sure that we are very clear on what we're doing so we don't get confused afterwards. So in our case, I want to propose that we apply 1/3 of the total and rate as at pre-plant or near planting. So to do that, we just give it an equal sign here on this column, and I want to take the total nitrogen adjusted rate. And if I want to apply 30, or if I want to apply a third of that at pre-plant, what we do here is basically multiply that adjusted by 0.33, right? That gives us 33% of the total. So if we run that, and we print that object, now we have another column, right? The one that we just created for the pre-plan rate, where for the high yield zones applying 56 pounds of N per acre, for the low yield zones applying 47 pounds of nitrogen per acre. Of course, here, because we are applying 33% based on the total N rate, which is based on the yield potential of each one of the zones, we are getting different pre-planned nitrogen rates. And our goal here is really to apply a variable rate in season. That's the main timing when we would apply in season. First, because it is the largest rate that we are applying between the pre-plan and the in season. So it has a larger impact, and also it's when the crop needs the most. And so what I want to propose here is, so let's say if you're working with this producer and they have the capacity to apply a variable rate in season, and perhaps they really don't care about applying variable rate pre-plant. So what I want to do here is basically just assume that our pre-plant rate to be equals to the lowest N rate among the two zones. In this case, they're not that much different. So I'm just going to move forward applying the lowest of the two rates to both zones pre-plant, and let the remaining be applied variably in season at side dress. Okay, so with that, let's just add another pipe here, come after this next comment here. Let's do a mutate. And here I want to call this column IS for in season, underscore total and rate, underscore ADJ for adjusted, underscore pounds per acre. So here we're going to calculate the in season nitrogen rate, right? So if you think of it, the in season is basically going to be the total that we calculated, right? So this total adjusted, so adjusted because it was 25% higher, assuming cotton after cotton. So it's basically that total minus the in season. However, I don't want to simply, well, you know what? I don't think I ran this. So let me just stop there and run so we can see the pre-plant rates and print it. Just want to print that. So we have, as you know, as we can see, we do have like two pre-plant rates, right? Which we just talked about. And my recommendation was that we apply a fixed rate pre-plant and only do variable rate in season. If we're applying a fixed rate pre-plant, let's just go with 47 pounds, which is rounding the lowest rate here. So if we just do the total N rate, which is changing by different zones, and just deduct the fixed rate at pre-plant of 47 pounds, this is how we would represent that in code. And if we just go ahead and run it, and now print it, our in-season, which is really what we need to give this producer here, is varying, right? So this one is actually varying. The pre-plant, even though on the column here says differently, but we calculated the in-season by using a fixed deduction of the pre-plant rate of 47, which represents the amount of the lowest yielding zone. So this is how we would do that, and this is our total nitrogen rate that this grower can apply variably in season, you know, and to those two different zones that we created. Okay, so here's the thing, right? Normally, even though, you know, we're calculating on a nitrogen rate basis, but normally producers want to know what is the rate of product that they will have to apply. And one of the most common sources of nitrogen or product of nitrogen is urea ammonium nitrate solution that is a liquid fertilizer that has a few different concentrations that you can find on the market. Some of the most common that I've seen are ranging from 28 to 32% nitrogen, but there may be other concentrations as well. And I guess the main goal here is just to understand that there are different nitrogen sources, and those sources have different concentrations of nitrogen in them. So every time that we're going from a rate that is in pounds of nitrogen per acre, and we're transforming that into a product rate, so not just nitrogen, but a product, so like a rate of UAN, we do have to consider a few things. And one of them is how much nitrogen there is in that source, because they all are different, right? So that's what we're going to do here next, because I do want to provide this grower with a recommendation of how much gallons of UAN 28% per acre they have to apply, and not just pounds of N per acre. Okay, so to do that, how do we do that? How do we go from pounds of nitrogen per acre to gallons of UAN per acre? So we're going from weight to volume, right? So how do we do that? There are a few different things that we have to consider here. And before we actually show you the formula, I just want to go below on a next chunk where we're going to make some calculations. Okay, so here's what I want to ask you, or I want to tell you and then ask you a question. UAN is a liquid fertilizer. How do we go from, or how do we get to a volume of a solution if right now we have a weight measure, which is pounds of nitrogen per acre? What information do we need to make that conversion? I just want to stop for a brief second here and let you think about that. If we were in class, this may have been a quiz, but since we're not synchronously today, I just want to give you a moment to think about it. So the piece of information that we need here is to know how many pounds of nitrogen there is in a gallon of UAN. To do that, before we get there, we have to know how many pounds of UAN there is in a gallon of UAN. So that's really the key information that we would need here. We can find that information if you just Google. Some of the fertilizer manufacturer companies have the fertilizer label or maybe the MSDS information online, and we can find that. So a couple of different sources that I'm providing you here with the websites. I'm just showing you here a few of them that, if we just go to one of them, let me just go to this first one. And I found these websites just by Googling, pretty much, like UAN 28% density, I think is what I was Googling. But if I just launch that here, so this is the safety data sheet of urea ammonium nitrate solution, and it is 28%. One thing to keep in mind is even within the same source, if that source is liquid like UAN is, the number that we're after will change depending on the concentration of nitrogen in that source. So be aware of that if you're working with a different concentration of UAN, you have to be specific of what concentration UAN you're looking for to get the right number. But basically what we're looking for here is, let's just scroll down here and see. So they're just giving a lot of information about this product. Let's see, we're looking for the physical properties of this source. Right, so right here, we say they're giving us that it has a density, that's what we're after. So it's giving us a temperature range, so at 16 degrees Celsius, 28% UAN has a density of 10.67 pounds of UAN per gallon of, so a gallon of UAN basically weighs 10.67 pounds. And then gives us another, so here's where I was saying that depending on the concentration of nitrogen that you're looking at, that density changes, right? So For UAN 28% at 16 degrees Celsius, the density is 10.67. However, for UAN 32%, also at 16 degrees Celsius, that density is 11.08. So that's just, just to keep that in mind. But the number I'm after here is this 10.67. I believe, if you go to different sources, even this number may range a little bit, and that is because of the temperature assumed for that calculation. The hotter it gets, the density decreases, right? So this number may change a little. You may see like 10.6 perhaps is one of the most commonly used, but I just wanted to show you a source, and we're going to use this number here, 10.67, to follow up. So if we return here, so UAN 28% nitrogen density in pounds of UAN per gallon of UAN. Let's just use the assigned symbol here and say that that's 10.67. And again, this number here we got from the safety data sheet of the product from a specific company that sells UAN 28%. Now, now we need how many pounds of UAN there is in a gallon of UAN. But to really make our conversion above, we need to know how many pounds of nitrogen now there is in a gallon of UAN. So we know for that we need to know the concentration of nitrogen in UAN. In this case, here is pretty straightforward. It is 28%. So the way that we express that is by saying 0.28. So now to know the pounds of nitrogen in a gallon of UAN, we basically just have to multiply, right? So we just multiply. So I'm just going to run these two objects so I have them in my environment. And now we basically, to know the pounds of nitrogen per gallon of UAN, we just multiply both of those objects. Right, so I'm just copying the density one and then the percentage concentration, and then multiplying one by the other. And then I'm just going to print this object that was the last one I created. And this gives us like almost 3. So it's basically saying that we have 3 pounds of nitrogen per gallon of UAN 28%. So this is the number that we needed then to finally go from pounds of N per acre to gallons of UAN per acre. So now now that we learned that we found this number here, let's just go back to the chunk above and now calculate the gallons of UAN per acre for these 2 different in-season rates that at this point are in pounds of nitrogen per acre. So if you come here, add your pipe, and we're gonna use another less mutate here to do this. So let's use a mutate. I want to call this column UAN rate underscore gal AC for gallons per acre. So this is pretty much going to be our in-season rate that we just created above. So if you want to copy that name and paste it here, divided by 3. And again, this number here, 3, is coming from the chunk below that we just calculated that. I'm just rounding that to 3, but this is where it is coming from, right? So if we go ahead and run that and then print it, these are the rates of UAN that this producer will need to apply on a gallons per acre unit to each one of the zones. This is a very broken number. I just want to round this to be easier to visualize it, and also to be more sensible when we're telling a producer what rate they're applying, right? They don't really need to know those many decimal points. So after that 3, I just want to add a comma. So I am still within the mutate. I just want to basically overwrite the column we just created, and I want to round. So you should be thinking that we're using the function round. We give the column that we're rounding, and then how many decimal points after that. I just want to give it 1 decimal point. So if you run it and you print it, this is what you should be seeing now. Your UAN rates in gallons per acre for the 2 different zones are 41.3 and 31.7. So this would basically, on this object here, we basically have the rate that we need to give this producer, right? However, we also need to have this information here in a, well, but let me take one step back and just print this again so we can look at it again. So this, again, is a rate on an acre basis, right? So now, this producer may be interested in knowing what is the total amount of UAN they would need for that field. And if you think about it, the total amount of UAN is basically the rate times how many acres they have. In this case here, because it is a variable rate, it means that we have two different rates and also two different areas corresponding to each one of the zones, right? So for us to tell them how much total UAN they need, we need to consider both of those pieces of information. So if you come to the next chunk here, that's what we want to do, is calculate that so we can provide this information to this producer. So this object VRN, it is, even though it only has 2 rows, but it is still a geospatial object where it has still that geometry, which in this case here is basically only 2 rows. So it's not giving us necessarily the pixel by pixel polygons, but these polygons still represent the total of each one of those zones. So what we can do here is basically calculate the area of those 2 zones with this object. To do that, let's just start doing that here. You would add a pipe. We're going to use a mutate because I want to create a new column that is going to have the area. I want to call that column area underscore M2 for meter squares or square meters. And the reason why this is going to be square meters is because of the projection or CRS of this layer. So again, another reason why it's important to have your CRS projected into a meter projection and not just have as WGS84 and in degrees. Because now we're calculating area, we really want that to be more precise. And for that, we need for the CRS to be in meters. So we come here and there is a function with the SF package that is called st underscore area. So this is what we're doing. I believe if you run this way, let's see, it gives us an error. And it's basically just because it's not understanding what we're calculating the area of, because we're using the pipe here. So for some reason, the VRN object is not falling in here. We just to override that behavior, we just add a dot here, and that indicates the pipe that VRN should be placed right there, and so it would work at that point. So if we run this, it ran all right. We go to the end. Now we have this new column that is area in meters squares, and this is how much area we have for each one of the zones. And this is the total area of each zone, right? So again, it's not the area of each polygon or each pixel anymore, it's in the area of the whole zone. Now, it is in meter squares again, because that's how the projection units are set up, but I do want to transform this to acre, right? So let's just add another pipe, start typing mutate. I want to call this next column here area underscore AC to mean that it is an acre. And basically what this would be is just that previous column that we created. So area in meter squares divided by 4047. That would be the conversion factor here. If you run this, we have now this other column here that is area per acre. So we see that the high yielding zone is about 52 acres. The low yielding zone is about 47 acres. So they're pretty close in area. And even though here still shows M square, so M meaning square meters, but we really know it's not, at least not this column, right? Because we have already converted, but it's just the behavior that this column is having for some reason. To override that, I just want to force this this column here to be numeric. So right now it's in the class is units, and I just want to force that to be numeric. So we would come here to the code and just add as.numeric. Make sure you close all of your parentheses there, and this should get it back to just a numeric column. Yeah, so now we went to double again, and this is just a number. Now it's not in any specific units as the area meter squares is. And the reason also for that is just the default behavior of the st area column. It just gives that new class of a column and just sticks with it. So I just wanted to override that. Okay, so what I want to do here is the next thing. So let's just add a pipe, come after this comment here. And I do want to extrapolate our area in 20%, just so we get 20% more area and therefore 20% more product as well, just to be on the safe side, just to order a little bit more, right? So here, if I want 20% more of the current area, let's use a mutate. I want to call this, I'm just going to override that same, or I'm sorry, we're not overriding anything. We're creating a new column called UAN_gal. So total gallons of UAN, it's basically going to be, well, let me just take a step back here and ask. I guess on my explanation, I skipped this step, so I just want to return to it. So now we have our total area, right, per zone, which is this, and we also have our UAN rate on a gallons per acre unit, right? If I want to know now how much total UAN I need for each one of the zones, so not thinking of a zone polygon anymore, but or a pixel anymore, but thinking of the entire zone. How do I do that? You know, what do I have to do to get to that point? And if you're thinking about it, you know, basically we just need to multiply, right? We need to multiply the rate by the total area, and then with that get total gallons per zone. So let's just go ahead and do that. So I want to do UAN gallons per acre times area per in acre, right? So area AC. I just multiply that, and we just scroll to the right here. This is the total UAN. So not a rate anymore, a total absolute number of gallons that we need for each one of these two zones. And what I was telling you before, that I wanted to multiply this by 20% more, just so we have extra, is we would come here, I would just add a parentheses in the beginning. I mean, we can keep this last one, we just have to add another one in a bit here. But to get 20% more, we just multiply this number by 1.2, right? So that just gives us 20% more of what we had already calculated. And don't forget to close that parentheses right there. So now if we do this and we run it and we just go to the end, our total UAN per zone that we need in gallons is this, right? So again, not a rate anymore, because a rate is based on a quantity applied but per area. Here we're just getting the total quantity that we need for this, for the area of these two, the total areas of these two zones. Okay, so when we're telling the total area, the producer doesn't really care how much per zone. They just want to know the final number, right? So how could we basically sum these two numbers to give a total over the two zones, and just have one total number to say this producer, this is how much gallon you need for this field, regardless of zones? You know, every time I'm telling you that we need to get more than one column and give one column, like we have an initial number of rows that we're decreasing, I hope that you're thinking summarize. In this case here, we don't have to group by, because there's really no group by. The group in this case would be the entire field, so basically no grouping. So we can just use a pipe here. We're not going to have to group by again, but we are using the function summarize. So remember, the function summarize always returns you less rows. And if you don't group by anything, it's going to return you one row only, because the summary of the whole data set. In this case, the whole data set only has 2 rows anyways, but that's what's going to do. So let's call this column total UAN underscore gal for gallons. Let's give it an equal sign. And so if I want to combine or add these two rates, what function do you think that we would need? I hope you thought of the function sum. And maybe, I don't remember now if we already used this in the class previously for you to be already aware of. So if we have not, then maybe you weren't thinking of this function anyways. But we want to use the function sum. So we just want to ask for the sum of the column UAN gal. If we run that, we do end up with only one row, right? Remember, that's because of the summarize without a group by only returns you a summary of whatever you ask for the entire data set. So here we have the sum of those both of those amounts of UAN gallons for this field. And I just want to round this up as well to make it more straightforward when we're telling a producer about this. So let's just add a comma. It's still within that summarize. I just want to call again this column name total UAN underscore gallons. So we're just basically override it, and then use the round function on that same column, total UAN per gallons, and then give it a comma and say 0. So here, it's a total gallons of UAN. We're already asking for 20% more, so we don't really need to be super specific or super precise on our decimal points. So just a 0 here is enough. This is how much you would tell this producer to how many gallons of UAN they would need to have at least for this field here to be able to apply, to do the in-season application based on those 2 zones. This number is what you would give that producer. So this chunk basically summarized doing that, right? Getting that final number and giving this to the producer even before the application happens, because they have to have this by the field when they're doing the application. All right, so we have a few more steps here. So one of them is, so if you think of it, I want to create an object where we have the zones and we have the rate for each one of those zones. If we think of all the objects that we imported, the one that has the zones is the one that has everything, including the zones, is called ZoneYield, right? So this is what ZoneYield looks like. It has the zone column. It has 4,032 rows. So that's the one that we need to give, where each one of the geometries is like a small pixel, a small polygon, and that has the zones, right? So let's just use this object. So if you come back to the RX map here on the side, I want to create this new object called vrn underscore v. So we're going to give the variable rate action rates as a vector file. Let's give the assignment symbol, and I want to start with zone underscore yield, right? So again, if I just run this and print, it's the one that we just saw above. And I want to bring here, so my goal next is to bring here a column where we're going to have the two rates, right? So basically what I need here, what I want to have is all of this information, but especially the UAN rate in gallons per acre. So this information right now is in the vrn object, which again is this one that only has 2 rows. And really what we need here is to merge the other object that has 4,032 rows with this one, basically using the common column zone. So it's going to use this column here to make the join. And really what we're after at the end is just this rate here. So we could do a join, we could do a case when. So there are a few different ways that we could get to this, but I want to show you by doing a join. So if you go back again to the to this chunk right here, so the RX map chunk, if you're browsing on the side, you want to start with a ZoneYield, give it a pipe, and then we're going to do a left join. So even though both of them are geospatial data, but I want to do a left join, and I'll just show you why in a second here. So let's go ahead and use the left join function. So remember that in the past, we had used stjoin, which is for geospatial objects. This case, if there are also geospatial objects, but they don't have anymore the same number of rows, right? Because one is a summarized data set. So I just decided to use a left join because of that. So here we want to left join with VRN, right? And just to remind you, VRN has this. And I want to drop that geometry from the VRN because right now that geometry is not going to play a role on this join, right? So to drop geometry, as we have already seen in a different exercise, I'm just going to add a pipe here and then just use the function st drop geometry. So I want to run this only so you see what that does. So this basically turns that VRN into just a data set. So no geospatial information at that point. And if we do a left join between just a regular data set, which now this is, with whatever other data set, the left join is going to look for a common column to make the join. In that case, the common column is zone. So zone is both data sets here have a column called zone, all lowercase. And inside that column, both data sets have values high and low, all lowercase as well. This is the reason why we can join them without a geospatial component, but just based on a column that is shared. So if we do that, it tells us here that it's joined by zone. So it was able to already find that common column for us. And then it made the join. So if now print VRNV, it should still have 4,032 rows. It should have all the columns coming from ZoneYield, which are all the yield ones, and also the zone one. And then in the end now is going to have all the calculated variables that we calculated on the VRN object above, which is just repeating out a lot of that, right? Because it only has two values, one for the high, one for the low yielding zone, just repeating out that whenever that value matches that zone. And really what we need here is the rate, but also, having the geometry of the 4,032 cells, because now we're going to use that to both plot first, but also export this to a producer that can use this information to direct their variable rate equipment. All right, so to do the plot here, I believe I left you all the code already. So we're not going to have to do much. I just want to show you that I'm taking that object we just created. I am transforming that UN rate to a factor. And the reason I'm doing that is because the rate, there are only two levels of rate, right? It's just the high and the low. There's not like a continuum of them. And so that just helps us for the legend to be binary, to be two colors instead of giving us a gradient, which doesn't make a lot of sense here because we only have two rates. So that's why I'm first transforming UN rate in gallons per acre to factor, and then just bringing a ggplot using geomsf because this is an SF object, and then doing the fill in color according to that UN rate in gallons per acre. I'm just changing here the titles and how the legend appears as well, just giving the theme. So if you run this, this is what it would look like. This is basically what the producer would be seeing when they're applying this variable rate in season, right? So I'm saying here it is a variable rate nitrogen prescription using UAN 28%, and these are the rates that are being applied to the two different zones, where we have the in gallons per acre varying between the low and high yielding zones. I also left you the code here to export this figure if you wish. I'm exporting that on my side. If you want to export, just go ahead and run that. And then lastly, to wrap up this exercise, okay, so we went through all the calculation and found the rates, But now we need to export this so a producer can use this data set with their variable rate equipment. So that's the last step that we're going to do today. Because now we are exporting this for a producer to use, most commonly, their variable rate equipment software will take in a shapefile. To tell the truth, I don't know if it would take a GeoJSON. Perhaps it would, but I know for sure that it would take a shapefile type of geospatial file. So this is basically going to be the first time that we're going to export something that we did as a shapefile. And again, that's because we can give this to a producer and they can use it on their software. So if you come here to the next chunk, we're already starting with the object VRNV right there. I do want to simplify this data set. So if we just print VRNV, it has like 11 columns. That producer doesn't really care about any of the other columns. The only two they need is the zone and the geometry and the rate in gallons per acre, right? That's what they really care about. So to just simplify this a little bit, let's select those columns. So if we just give us a pipe there, let's use a dplyr : select. I want to select the zone because that's the name of the zone, so they know what it is. And also the UAN rate in gallons per acre that is at the end of it, and the geometry. So if I just run that, this is what we end up with. So it's still the same number of rows because select is just selecting columns. It's not doing anything with rows. So we should have the same number of rows. And then those 3 columns right there. And then just go back to the code, add a pipe. Let's export this. So we are exporting an SF object. I hope you're thinking that we need the function write_SF. So the data is already coming through the pipe, so we don't have to tell a data object name here. Just going to give it a path. So if you open and close quotation marks, let's do .. to get outside of the code folder. Let's go inside of the output folder. So now we're creating a data to be outputted. And before we continue here, I just want to ask you to do another step. So if you recall, and you're going to see that in a moment, if you don't recall, shapefiles, when you export a shapefile, that actually exports, I think, at least 4 or 5 other accompanying files, and sometimes even more than that. And if we just, so I came here to my files tab, I want to click that R blue button, and I want to browse to output. If we just output that right here, I mean, we could, right? But think that perhaps you created multiple plots and exported other data sets, and then you export a shapefile as well. It becomes kind of cluttered to have the shapefile and all of its accompanying files mixed with other files that perhaps are not related to that. So what I want to ask you is, let's create in here a folder that we call VRN, and then we can save the shapefile only inside of that folder and not have it mixed with other output files. So again, I just want to refresh your head. If I come here on the R blue button, I want to go inside output, and this vrn.png is that figure that we created above. So inside of output, I want to click this button to create a new folder. I want to call this folder VRN, all uppercase, and say OK. So that way we create a folder now inside of output that's called VRN, and I want to export this shapefile inside of that folder, right? So all of those shapefile accompanying files are by themselves in one folder and not mixed with other figures and tables and other data files that may be in the output folder. So now if we come back to the code, if we hit tab, so I got outside of the code folder, I went inside the output folder, and if I hit tab now, I should see that VRN folder that we just created. So we can go inside of that, and here's where we export our file. So I want to call this file VRN, all lowercase. And if you recall, before we're just saying whatever name we were given, we're just saying .geojson. Here's going to be a difference, right? So we're going to say .shp for shapefile. Regardless if this is a shapefile or a GeoJSON or other file, always remember to change that delete DSN behavior of write SF function. To do that, we add a comma here. I just want to break code to make it easier to see. And the argument is called delete underscore DSN. I want to say equals to true. So if you run this, it actually gave me an error. I'm not sure why. Let me see. Well, it's still created. So if I come here, right, so on the main folder of the project, go on output, go on VRN, still created 4 files there, where one is the SHP and then 3 accompanying files. So they're all there, even though it gave me an error here. If you do get an error on your side, make sure you check if it has outputted to the files to that folder. If it has not, let me know. I can help you troubleshoot that. On my side, even though it gave me an error, it still went through and saved the file. So that's what we needed. And this again, just going to the files here on the shape files, I just want to demonstrate to you again why my preference for GeoJSON, at least when I'm working within my own projects and not exporting something to someone else to use. So we asked to create a shape file, which it did, but it also created 4 other accompanying files with that. So when we share these files with a producer or with anyone else, we have to send all 4. If we only send the SHP, they will not be able to see it properly on their side and not be able to use it. We have to send all of these files to that person. Okay, so this is pretty much all I had for today. In summary, we basically first learned and understood where to look for information on crop and also nutrient-specific recommendations, in this case for Georgia. We defined the yield potential for each one of the zones as being the 90th quantile of the yield distribution for 3 years. Then calculated variable rate nitrogen, both in pounds of nitrogen per acre and also in gallons of UAN. Sorry, this says 38, but it's 28% per acre. And then finally exported that as a shape file that we can share with the producer and they can actually use that on their side. This is the entire workflow. I want to save my script here. And I just want to tell you that this basically wraps up the major part of this course, which was going all the way, if you recall, when we started with the raw yield data and then cleaning, wrangling, processing, interpolating those layers, and then doing the spatial temporal analysis to understand the yield changes over time and also space. And then finally bring in the terrain data, the elevation data, doing all the secondary variables, interpolating them, also doing the EC data, cleaning, interpolating that as well, creating the zones, processing those zones, validating the zones, understanding what they mean, which zone was high, which zone was low yield, and then finally creating a prescription for those zones. This is a very common workflow in precision ag. In this case here, we're talking about nitrogen, but you could have used a similar framework if we're talking about any type of variable rate of anything, really, right? It's just you may require some different variables that we didn't collect here, right? So let's say if you're planning to do variable rate seeding, perhaps you would use other layers to define those zones. Perhaps if you're doing variable rate chemical applications like pesticide application, you will need to have other types of layers coming in to help you create those zones. But the overall framework is still the same, right? It's still bringing data, getting them to the same spatial extent, doing interpolation, doing cleaning, and then at some point doing the zones. In this case, we learn how to use k-means for that. So using k-means, defining the best number of zones, and so on. So this overall framework of programming, but also thinking about layers that you need, steps you need to take to get to a final prescription, which if you think of it, we did all this all, for the half of the semester or even more than that, just to create this layer. Let me just print that map again. So everything we did was because of this, right? To get to this point and be able to give that producer a layer that they can use for doing variable rate and giving them the rate that they can use on those zones as well. So this basically wraps up this part of the course. And I will be recording another video to tell you about the final project, right? So the final project is going to be required for all students. I will have some extra questions for graduate students in there, and undergrads can use that as extra credit. But yeah, I'm going to give you more information about that in the next video. I guess this is what I had for you today for this exercise. So we'll wrap up with it. And then for the next couple of weeks, I think couple or few weeks, you're going to be working with Dr. Lacerda with processing UAV imagery. And then I will come back after that to show you how to use some of those imageries to do variable rate using imagery and not zones. So that's going to be the last classes or last lectures and exercises of this course. All right, if you have any questions, if you run into code issues, always feel free to email me, or if you have code issues, especially to post on GitHub. And that's all I had for you. So thanks.